All right, so we're just looking at more examples using Pascal's triangle. Notice every time I just have the triangle already sort of reprinted for us. So just so that we don't have to waste time kind of rewriting that. So anyway, this one's going to say determine the first 4 triangular numbers using Pascal's triangle. Well, we might not have heard of triangular numbers before, so I'll show you what those are. It's basically the numbers you get if you create a triangle using dots like this. And you'll kind of notice, okay, first there's 1, so then we have 2 rows, 3 rows, so the next one's going to be 4 rows, but also the bottom row always has however many dots for, this is our first triangular number, our second, our third, so that many dots are in the bottom. So our fourth will have 4 dots down here, and then 3, and then 2, and then 1. So what the triangular number is just however many dots there are. So this is 1, there are 3 in total there are 6 in total there, and then 10. I'll do one more of these just so we can get the pattern down in full. So 5 for the bottom row, and then 4, 3, 2, 1. And so there are 15 of those. Notice that each one of these is just the previous one, but with a new row added below it. So if I took the 4th triangular number 10 and this picture, if I just add a new row below it, that would give us those bottom 5, and then it would make 15. So how do we find that? Somewhere here in the table. 1, 3, 6, 10, 15. Oh, actually, it looks like this is just the 3rd diagonal, right? The first diagonal is all 1s. The second diagonal is just our counting numbers. The 3rd diagonal, these are our triangular numbers. So without even going through kind of the next list, we could say, well, what's the 6th triangular number? The one that comes after this is going to be 21, because I see in the diagonal it's the next thing. And of course, this triangle keeps going. So if I wanted to find the next number, it's going to be 7 plus 21, so it's going to be 28. So we could do that. This one asked for the first 4 triangular numbers, so I had written those out for us, right? Showed us what they were. But from here, we can just see it's 1, 3, 6, and 10, right? Same that we got over there. All right, we also recently talked about Fibonacci numbers, so we can find the first 4 Fibonacci numbers. Now, again, some of these are just verifying, right? So we know that the Fibonacci sequence starts off 1, 1, and then we add the previous 2 numbers. So 1 and 1 makes 2, 2 and 1 makes 3, 3 and 2 makes 5, and then we get 8, 13, 21, 34, and so on. So this one's a little bit different because we are looking at diagonals, but we're kind of looking at slightly, I don't know, strange diagonals, I guess I might say. So the first one is here, right? So we just add the things that we pass through. It's just 1. The next one is here, also 1. But the next one is this one. It passes through 1 and 1, so that makes 2, right? That's our 3rd number. The next one, and I'm just trying to use alternating colors for clarity, passes through 1 and 2. So we should be passing through every single number as we go down, but the diagonals are just a little bit off center. So the next one, for example, would be 5. The next one should pass through 1, 4, 3, right? It skips 1 here, so we don't pass through a 1 on the far diagonal every time. So 1, 4, and 3, there's our 8. 1, 5, 6, and 1, there's our 13. And sorry, these are a little wavy, but that's kind of the idea. You can certainly search this and find some slightly better visuals, right, that aren't drawn by hand on here, and it'll be maybe a little bit more clear. So we could ask for just, what is the 10th Fibonacci number or whatever. Sure. Another thing we might ask is, what do we have to add in order to get something like, the 6th Fibonacci number? So what do we have to add to get 8? Well, in this case, right, we look at our diagonal here, we added 1, 4, and 3. All right, so we could ask questions like that, so that's something to keep in mind. All right, and then the last type of application we're going to look at is something that goes, again, way back earlier in the course when we were doing combinations. So this is just another way of writing combinations. But the more common way maybe that we have seen those is like this, NCK. So from n objects, choose k of them or combine k of them. Remember, this takes us back to our old friend factorials. We also have an Excel function that calculates these for us. So just to be clear, so 5, 3, this is not a fraction, right? We don't see a fraction bar. So this is just saying n is the top number. So of the 5 elements or of the 5 items we want to choose 3 of them. So k is the bottom number. So again, we've calculated these with factorial. So we've done this as 5 factorial over, well, k factorial would be 3 factorial. And then n minus k, so 5 minus 3 would be 2 factorial. Right, we don't really need parentheses there. But the idea is for these pieces, we can look at going through the different combinations. So if we have something like, let's suppose we wanted to think about all the different ways we could do 5 choose something. So I could combine no objects. I could combine one object. Oops, not a fraction. Right, easy to make that mistake. We're so used to making fractions. Okay, so 5 choose 1. I can do 5 choose 2. The ones we're interested in are choose 3, choose 4, and of course the very last thing, of 5 objects I could choose all 5. So this is kind of like the sequence of all possible ways if I have 5 objects to select 0 of them, 1 of them, 2 of them, 3 of them, 4 of them, or all 5 of them. So is there a row in here that has 6 numbers in it? Yes, it's this one. And in fact, we see that 5 is the second number in that row. So if we see 5 in the top, we're going to use the row that essentially starts with 5, right? They all start with 1, but as far as numbers that are not 1, it starts with a 5 here. So we're going to use this row. And so all this means is that 5 choose 0. So if I have 5 objects and I want to choose none of them, that can be done in one way, right? You can do nothing in only one way. If I have 5 objects and I want to choose one of them, that means I just have 5 different choices, right? I can choose each one of those objects. 5 objects and I want to choose 2 of them. Again, combinations say order does not matter. So there are 10 ways to do that. Selecting 2 objects, that's equivalent to saying not selecting 3 objects. And that's kind of what 5 choose 3 looks like. So that's also 10. 5 choose 1, another way to think about that is choose 4 objects to leave out, right? So you can choose what you are selecting or what you are not selecting. So that's why we get this kind of symmetry going on. And then of course 5 choose 5. Well, there's only one way to choose all of our objects, which is 1. So this gives us the entire row, but all we were asked for here was 5 choose 3 and 5 choose 4. So the ones that we wanted were just these 2, so 10 and 5. But it doesn't hurt to know kind of how to work with the whole row. Okay, so then if we have something like this, determine the values of 7 choose 2 and 7 choose 4. Well, we know that we can just pop down here, because we see that this is the one that starts 1, 7. So, okay, 7's good. Remember that we start off with the very first one is going to be 7 choose nothing, right? So if we want 7 choose 2, we got to go 2 spaces over. So here's 7 choose 2. The next one would be 7 choose 3. After that is the next one we want, 7 choose 4. Okay, so 7 choose 2, 21, 7 choose 4, 35. And that's that.